With the introduction of transformers, the landscape of AI was forever changed. But what exactly makes these models so powerful? To understand that, we need to look at their architecture. Now, let's break down the components of the transformer model and see how they work together to process information more efficiently and accurately. In a transformer, the basic architecture follows the encoder-decoder structure, which is the foundation of how the model processes and generates data. Let's first talk about the encoder. You can think of encoder like the process of encrypting a message. Its job is to take the raw input, in our case something like a sentence, and convert it into a form that the model can better understand. Imagine you are trying to send a secret message in a game of telephone. Instead of sending the exact words, you encrypt the message into a code that can carry more meaning and context. The encoder does this by processing each word in a sentence and paying attention to how each word relates to every other word in the sequence. For example, take the sentence, "The cat sat on the mat." The encoder doesn't just process each word in isolation, it looks at the relationships between all the words, cat and sat, mat and on, etc. This way, the model learns that the cat is doing the sitting and the mat is where the cat is sitting. What makes this unique is the self-attention mechanism used by the encoder. Instead of only focusing on the word immediately before or after, as RNNs would, the transformer's encoder looks at every word in the sentence at the same time. It assigns different levels of importance or attention to each word depending on how relevant it is to the current word being processed. So, when looking at the word sat, the model may give more attention to cat and mat because these words are more related in the sentence. This allows the model to gather context efficiently no matter where the words are in the sequence. Now, let's move to the decoder, which is like the process of decrypting that message into something meaningful. Once the encoder has processed the input and created an internal representation, the decoder takes over and generates the output, such as translating the input sentence or predicting the next word in a sequence. For example, if we were trying to translate "the cat sat on the mat" into French, the decoder would take the encoded version of that sentence and predict the French equivalent as shown on the screen. Again, what's crucial here is the self-attention mechanism, which allows the decoder to look at the entire encoded message and determine which parts are most important for generating the next word in the translation. But the decoder also uses encoder-decoder attention, which means it looks back at the original input, the encoded message, and decides which part of the input is most relevant for generating the next output. When predicting chat, which is French for cat, the decoder attends to cat in the input to make sure the translation makes sense. This powerful two-part process, encoding and then decoding with attention, makes transformers highly effective at understanding and generating complex data. Now that we have a grasp on how the encoder-decoder structure works, let's dive deeper into the core feature that sets transformers apart, which is the self-attention mechanism. This is where the real magic happens, allowing transformers to handle complex relationships between words in a way that older models couldn't. At the core of the transformer model is the self-attention mechanism, which fundamentally changes how we process sequences like text. Traditional models like RNNs relied heavily on the order of words, processing them one by one. However, transformers revolutionized this by allowing each word in a sequence to look at every other word simultaneously. This helps the model capture relationships between distant words that are hard to connect using older methods. Let's break this down with an example. Take the sentence, "The cat sat on," as shown in the diagram. In a traditional model, the word cat might primarily rely on the immediate word sat. But in reality, To fully understand the sentence, cat also needs to consider the other words of the sentence, which are on, the, and mat. Self-attention makes this possible by allowing each word to look at all the other words in the sentence. In the diagram here, we can see that the word the is connected to all the other words in the sentence except itself, and similarly, the word cat is also connected to every other word except itself. So, when the model looks at cat, it can also recognize that mat at the end of the sentence is relevant to understanding the scene being described. Now, let's dive into the math behind self-attention, which revolves around the concept of query, key, and value vectors. Every word in the sentence is converted into these three vectors. Query represents the word that is trying to gather information. Key represents the words being considered, and the value holds the actual content of the words. Self-attention calculates the relationship between words by taking the dot product of the query and key vectors. This score determines how much focus the word should place on another. Mathematically, it looks like the equation as shown on the screen. Here, the dot product between Q and K measures the similarity between the query and the key. The score is scaled by the square root of the key dimension dk, which represents the dimension of key vectors, to ensure stability in large vectors. Then, a softmax function is applied to normalize these scores into probabilities. Finally, the result is multiplied by the value vector to create the final product. This process helps each word decide how much it should pay attention to other words in the sentence. Through this mechanism, transformers can quickly identify the most important words in a sequence, regardless of how far apart they are, making them highly effective for tasks requiring an understanding of complex relationships. Now we will look at multi-head attention. In a transformer, rather than relying on just one attention mechanism, the model uses multiple attention heads simultaneously to gather a broader understanding of the input. Each attention head is like a different lens through which the model looks at the data. This multi-head attention structure is what allows transformers to capture more complex relationships in the data. Let's revisit our example sentence, the cat sat on the mat. With the multiple heads, each head can focus on a different aspect of the sentence. One of the attention heads in transformer might focus on positional relationships between words. This head is concerned with how words are ordered in the sentence. For instance, it might analyze the proximity of cat to sat and mat. Understanding that cat comes before sat and is related to mat through the action of sitting. This helps the model to grasp the structure and sequence of words. Another attention head might focus on the semantic meaning of words. For example, this head understands that cat is an animal and mat is an object you sit on. It helps the model grasp the meaning of words and their relationships. In our sentence, this head might recognize that cat and mat are related through the action of sat, even though mat is further away in the sentence. Another head might concentrate on the broader context of the sentence. It takes into account how cat, sat, and mat interact within the entire sentence. This head helps understand the overall context, how cat is performing the action sat on mat, and the meaning conveyed through the combination of these words. So while a single attention mechanism might only capture one of these aspects, having multiple attention heads allows the transformer to understand the sentence more holistically. Each attention head generates its own set of query, key, and value matrices. This means that different attention heads focus on different word relationships. One might look at syntactic dependencies like subject and verb, while another focus on the spatial relationship. By attending to various aspects of sentence like meaning, position, and relationships, each head brings a unique perspective. In the end, all the heads are combined to produce a richer, more detailed representation of the input. It's similar to how examining a picture from multiple angles gives you a fuller understanding of it. Now let's break down the equation for multi-head attention, which is central to how transformers work. The multi-head attention mechanism is represented by the equation shown on the screen. Here, Q, K and V are the query, key and value matrices. Each attention head uses these matrices to compute attention scores and focus on different aspects of the input data. On the right hand side of the equation, each head represents a different attention head. Each head performs its own attention calculation, focusing on different parts of the input data. This allows the model to capture various types of relationships and features. After calculating the attention outputs from all heads, they are concatenated together. This combines the different perspectives each head has gained. And then finally, the concatenated outputs are passed through a linear transformation matrix, which is the weight matrix, to produce the final output. This step combines the information gathered by all the heads into a unified representation. Multi-head attentions gives transformer an edge in understanding complex inputs because they can focus on different facets of the data at the same time. This is what makes transformers highly effective at capturing intricate details, whether in text or even images, as we see with models like vision transformers. Now we'll look at another aspect of the transformer architecture, which is positional encoding. Transformers have revolutionized how we process sequential data, but they face a unique challenge. They don't inherently understand the order of words. Unlike traditional models that process data sequentially, transformers process all words simultaneously. This means they need a way to recognize the sequence or order of words in a sentence. This is where positional encoding comes into play. Imagine a conveyor belt in a factory. Each item on the belt has a unique tag that tells the machine exactly where it is in the sequence. Without these tags, the machine would not know the order of the items and would have difficulty assembling them correctly. Similarly, transformers need a way to understand the position of each word in a sequence. Think of positional encoding as adding a unique label to each word in a sentence, so the model knows the position of each word relative to the others. This encoding helps the transformer to understand the sequence of words, which is crucial for interpreting the meaning of the sentence. For example, consider the sentence, "The cat sat on the mat." Without positional encoding, the transformer would treat all words as if they were a part of a bag of words, with no sense of their order. Here in the diagram, you can see that the first word is being given a position which is represented by the number 0, and the position of the second word in the sequence is being represented by the number 1, which is then subsequently converted into a positional encoding. This encoding doesn't just tell the model what position each word is at, it adds a numerical representation that helps the transformer understand the order of words in relation to one another. Now let us try to understand how it works. So the first step is to assign position tags. Each position in the sequence is assigned a unique tag through positional encoding. For instance, in our sentence, the first word has been given a positional encoding which is being represented by P1, and the positional encoding for the second word is being represented by P2, and so on. And then the next step is to combine these positional encodings with word vectors. These position tags are combined with the word vectors, so the representation of cat is adjusted to include both its semantic meaning and its position in the sentence. This combined representation allows the transformer to understand that cat comes before sat and mat, thus preserving the sequence's order and context. So, how does it differ from the previous architectures? The architectures like RNNs and LSTMs inherently process sequences step by step, maintaining a hidden state that updates as each word is processed. They understand word order through their sequential processing, but this can be slow and less effective for long sequences. By adding positional encoding, transformers enable parallel processing while still capturing the order of words. This approach allows the model to efficiently handle long sequence and complex relationships between words. This is the difference between the previous and the new architecture. Now that we have covered the major components from the transformer architecture, let us take a look at the architecture itself. In this diagram, you can see an overview of the transformer architecture. Here, I would like to mention that once the self-attention mechanism has processed the input, the output is passed through a feed-forward neural network where it undergoes additional transformations. This helps the model to learn more complex relationships and features. The same feed-forward network is applied to every position, but the inputs vary based on what the attention mechanism has learned. Finally, transformers use two important techniques: layer normalization and residual connections. Layer normalization ensures that the model's learning is stable and smooth by normalizing the inputs to each layer. Residual connections, on the other hand, act like guide rails, ensuring that the information can skip layers and flow smoothly through the network without getting lost. And with this, we have covered the core components of transformer architecture. But how do they work in practice? That we will take up in the next section.